Yes, no feedback? Okay, go for it.
Hello everyone and welcome to our final presentation of our Capstone project. My name is Kayla Pagat. I am a senior in mechanical engineering and I am the leader for our group.
My name is Logan Spencer. I'm a senior applied math major and I'm a researcher for our group.
I'm Brahma Patty. I'm a senior mechanical engineer major and I'm the designer in the group.
Hi, my name is Abofu. I'm a senior mechanical engineer and I'm the builder/coder for our group.
Hi, I'm Elizabeth. I'm a senior in computer engineering and I'm the communicator for our group. So a little bit of backstory before we get into our problem is we are working with an endotracheal tube. What this is used for is providing oxygen and other gases to the patient's lungs during surgery. And it also blocks bile or stomach contents and blood from getting into your lungs. So it's placed along like this, and this cuff will actually inflate so that way nothing can get into your lungs. A few key features of an endotracheal tube is the cuff, the Murphy eye, and the ventilator port. You guys all have a standard endotracheal tube that is being passed around, so you can see that during our presentation. So what our project is about. Our sponsor's name is Matthew Singletary. He is an anesthesiologist. What he gave us was that when removing a endotracheal tube after surgery, it rubs along what's called the vagal nerve in your throat, and that spikes the heart rate and your blood pressure when coming out, and those can lead to complications. So he wanted us to figure out a way to put a second port into the standard endotracheal tube, as well as to be able to administer medication to numb the throat, so that way when taking it out, those heart rate and blood pressure doesn't spike, while also keeping the key features of the endotracheal tube like I mentioned earlier.
So based on our problem statement from our sponsor, we came up with various customer needs. The primary needs primarily focused on making sure that the medication is able to be delivered to the patient within the specified region, making sure that we don't, we keep those essential features of the tube, like you mentioned before, the Murphy eye, the balloon cuff, as well as the balloon tube. Making sure that it's requires little to no training for the medical staff that are using it, so it seamlessly integrates with their day-to-day work. The secondary needs primarily focus on compatibility, so making sure that it works with current medical equipment, as well as making sure that it doesn't cost too much to manufacture, and making sure that it's able to withstand clinical trials. And the latent needs just focus on making sure that there's no airway interruptions in terms of flow within the tube, and there's no patient discomfort.
So for our end users, we have both primary and secondary end users. For our primary users, we have our patients who are going to be having that endotracheal tube down their throat, so we need to make sure that they have a comfortable extubation experience that'll minimize any discomfort and any other risks associated with that. And then also our medical staff who need a design that's going to be easy, reliable, and fast to operate with during those surgeries. And then our secondary end users are medical students, EMTs, and caregivers. And similarly to the medical staff, they need to be able to use that device on their patients during those situations. And then medical students also need to be able to learn and train with it. The relevance is that this device must meet legal and medical standards for patient safety and ease of use for medical personnel. So here are a few of our requirements to go into more depth with them. The top requirements are that the tube must deliver the medication to our targeted area, which is from the back of the throat, back of the tongue, to the cup area, which is about the vocal cords, and then it must include a secondary medication port and retain those key features such as the Murphy eye circuit port and balloon tube as mentioned earlier. Another requirement was that we had to validate that the medication delivery system was possible and possible through simulations and those physical tests of a model.
So at the end of this project, we're going to give our sponsor the following deliverables. So we do have our final working prototype that we're planning on giving to our sponsor, as well as the CAD model that they required, just that demonstrates the design of our idea. A math model that allows us to be able to calculate, because there are different tube sizes, calculate the holes as well as spacing based on various tube sizes. A flow simulation that allows us to visualize the flow as well as verify the exit velocity to make sure it's enough to reach the back of the throat, the trachea. We did do physical testing, as well as we're gonna have a comprehensive report that explains our design process from beginning to end.
So how do we actually tackle this idea? We use brainwriting to generate ideas, and we narrowed it down to 3 categories. And we ended up going with the third one, which is where we're putting slits on the top of the tube so that it'll act kind of like a sprinkler system for the medication. It'll spray up to the top of the throat and then run down the sides, covering the whole area.
So like Logan said, we ended up going with our third idea. To help us decide that, we created a Q matrix. So we compared the performance, ease of use, how easy it is to manufacture, and overall feasibility of each of our designs. With our third idea, scoring the best score with a score of 75, as well as our sponsor approved of the idea. So along with our Q matrix, we also created a QFD to relate our customer needs and our requirements. And the overall purpose of this was to get an overall idea of what to prioritize with our project goals in mind. What this ended up telling us is that our main priorities for our project was to add that second port to be able to administer that medication in the throat area, as well as maintaining those standard endotracheal tube components like the Murphy eye, the circuit port, and the balloon tube.
So now that we've decided on our idea, how are we implementing this idea? We start with a math model to decide on how many holes we need to put on the tube, as well as what size those holes need to be. And then we use the CAD model to visualize what we're making, as well as making sure what we're doing is actually feasible. And then we built the prototype using a CNC machine. So for the math model, we built our model upon the idea or the law of conservation of mass, making a function for the spray velocity out based upon the diameter of each of the holes, as well as the number of holes that we have. And then to verify that all this would actually work, we used the Reynolds number. So here are the results for the math model. On the left, you can see the spray velocity. The x-axis representing the size of the holes, as well as the different lines representing the different numbers of holes. So as the holes get smaller, it sprays much harder, and then as there are more holes, it's going to spray less hard. And then we use basic physics kinematics to convert that to spray height, just based upon gravity. To verify that our model is actually working, we use this tracker software where it goes through footage and based upon the frame rate and where it is, where each of what you're tracking is in the pixels is you need a position, and then using a linear fit, we used using a linear fit, we got the initial velocity as well as the initial position and acceleration. Next slide. So it looks a little bit silly, but because we're only looking at 5 holes with the holes being 0.6 millimeters, we only have 1 data point, and it may look weird because it's off the line, but that line is actually meant to be the maximum spray height. So we're basing the model upon the maximum flow rate for the syringe that we were using.
So once we had the math model finished, we then proceeded to CAD, and we had decided on an idea as well. We then proceeded to CAD it for visualization, as well as to verify that it was actually feasible. As you can see, this was our prototype. The idea was to basically keep the tube as it is and shift the current port like 90 degrees to the left and add our new port where the current port is, and as well as put the 5 holes over here. That way when you insert it into the person, gravity kind of helps spread it out as well. From this, we're then able to proceed to our ANSYS simulation. Over here we have an ANSYS simulation. So on ANSYS, it basically tries to focus on exactly where what region of flow you're actually focusing on. And since the tube is inside a tube, the only thing that we're actually doing on the flow, the only flow that we're actually analyzing is the actual catheter itself, where we have our inlet over there, as well as our 5 outlet holes. And what the ANSYS simulation basically did was verify our average outlet velocity, which is about 0.72 meters per second, was pretty close to our our experimental value. It kind of makes sense that was slightly off just due to like assumptions and stuff. As well as it also verified the maximum velocity kind of also correlated well with the maximum velocity from the math model.
Alright, so this is how the machine that Logan showed us earlier or mentioned earlier, this is the CNC machine. This is how we got our very precise holes within our catheter that is in the main tube. And then we also use this same machine for our final prototype.
So one of our requirements required us to physically test our prototype. And here at Florida Poly, we don't have any access to any medical equipment like that. And so to overcome that limitation, we reached out to Polk State and see if they were willing to help us. They did reach back out and they let us visit their lab. So pictured up here is a cross-sectional Airway model. This is the mannequin that we use to test our endotracheal tube design, as well as a video of them showing us their camera equipment that goes inside that model so you have a better visual of what's happening. So on the next slide, we have a demonstration of us testing out our final prototype. So in order to test this prototype, we ended up using water and blue food coloring because our sponsor said that the water is a very similar viscosity to lidocaine, which is a potential medication that could be used in actual applications. As well as this is also just showing that spray velocity is reaching those targeted areas in that throat area, which our sponsor was very happy with the results of this. So this is a photo of us working with some of the Polk State senior nurses. So this was a fun time to do that. Since we did know ahead of time that we were working with some of the students there, we did generate a survey to give them just to get some feedback. We did only work with 4 senior students, nursing students. So we took the average of the questions that we gave them, and that's what's shown up here is the average of those responses. And we really wanted that feedback, something our sponsor was really would like to get us on about, is not to make the design too complicated, not just for manufacturing capabilities, but also for it to be easy to use for medical staff. So what we got from this is that, if you go to the next slide, this is more, some of those more questions and averages, but they were very confident and comfortable with using our device because they were the ones testing it with their Medican, not us, as well as they really enjoyed the functionality and how our prototype ended up working.
So to actually come up with our final prototype, we went through various iterations. The first one being we tried to 3D print our tube, which originally we're thinking of using resin, but the size of the tube isn't big enough, at least for the resin printers here, unless we're doing it flat. So we decided to go with TPU, which actually came out really great in terms of flexibility. However, the support material, because you needed to use water to really remove that inside support material, since it came out, removed support materials at the ends. However, since there's no really holes over here to kind of allow the water to constantly flow, the material in the middle got really stuck. And when we tried to remove it, it just ended up not working out. So we then decided to primarily focus on working with the actual tube and just adding an extra catheter to really just show a proof of concept.
All right, so this is our final prototype. Our final prototype, we were able to add in, like Abofu said, that second catheter into the second catheter to support giving that medication. We also use that same CNC machine to poke the 5 holes that we got from the alpha prototype and have that catheter line still going to the cup to be able to blow it up. And like Abofu said, it's only moved 90 degrees over.
So some future recommendations and next steps that we wish we could have done given more time is that we would have collaborated with manufacturers to get more constraints and requirements to actually produce this in the medical grade materials, and then also to work with more healthcare professionals to validate the proof of concept through other clinical conditions.
Yeah, I have a question. So first a comment, I think it was really cool seeing this done in the medical field and seeing y'all's solution and the videos aspect of it. That was really cool. I did have a question about the use of the conservation of mass and then the density aspect. I know that they said that Lidocaine, was it?
Lidocaine.
Like that one. It's all, you said that's one of the medicine that's being used. Were you given any other medicine, and does the density affect the use of it?
The only thing, our sponsor wasn't our sponsor kept mentioning lidocaine, and he was okay with, he wanted us to only use lidocaine as, for viscosity for testing wise. He didn't want us to consider any other medication viscosity.
Yeah.
And we did talk to folks, she mentioned some other one, I can't remember off the top of my head. There are other potentials, there's not that many. But lidocaine seems to be like the main one that you would go with.
And the viscosity of lidocaine is pretty similar to water.
Water, yeah.
And that's what we use in the actual.
Thank you.
Do one more student question and comment.
I noticed this blue line going along the curve of the tube. What's that for?
That is for x-ray machines to be able to see where the endotracheal tube is inside of the patient.
Okay.
I'm just gonna ask, so with the extra holes, right, the whole point, actually, you know what, I'm not gonna ask this question. The only reason is because the cuff is supposed to cut off anything from going back up, right? So there's no chance of any fluids going into the holes that create.
Shouldn't be.
Okay.
And even if there is, our sponsor could say, the force of pursuing, just pushing it out would push it all out. Because the actual tube is separate from like the main hole,
Yeah.
so it wouldn't.
I just wanna make sure that there's no way.
And that was a concern, like when we did go to Polk State, some of the nursing students, they had that concern, but their professor, actually validated that because they thought it's not a worry.
Oh yeah, quick follow-up. With the video, it also hold at the bottom, is that okay?
Yes, so that is exactly what we wanted. We wanted gravity to hold everything at the bottom, and so that way it hit the top and then went down the throat, so then the lidocaine or whatever medication would then be able to spread throughout. And it's okay that it pulled on the bottom, because it's not, we asked our sponsor this, it's not, the amount that they're giving would be okay for the human body to receive.
To absorb it all?
Yeah.
Okay.
Joe, got anything?
Yeah, so again, how did you determine the optimal number of holes being 5? So exactly how did you decide that it was 5?
Can you go back to the graphs?
If you type the number and click enter.
So, we wanted it just to be like in this region. And it would have been helpful to put like a shaded region there to show you, but we just wanted it in this region, and a 5 holes was enough holes that like hit all of the areas in between. And also maintain enough like pressure and velocity to actually propel it.
Okay, and was any consideration given to the Reynolds number of the flow? So you said
Yeah.
viscosity wasn't an issue because it's similar to water, so you're not going to be iterating between. But did you care about it at all?
Yeah. If we go back one more slide, we checked the Reynolds number with that viscosity. It cancels out in the law of conservation of mass, but we did check the Reynolds number to make sure it was not turbulent.
Okay.
I don't show it, but I mentioned it.
Okay, so I have a comment, but it's not to your group, it's just to actually everyone who's not in my class. So how many of you are in Capstone? Great. Couple of you? Okay, so if you are, then I'm kind of talking to you, like, so they had, I think, 1 more week than you all did. They had their projects a week earlier. And so when you look at your other teammates and things, this is like what's possible in the time frame that you've already had. And so as you think about what your presentations are gonna look like a semester from now, right? Are they gonna look like this? In theory, they should be a little further along than these students, right? No offense to you, you'll do great, right? But just something to think about when you know, and you'll have been in panels too, when students blame their sponsors for things. I don't think, anytime you said something about your sponsors, it was to clarify or to say that this was a constraint, right? Just something to think about, yeah? And if you're gonna eventually take Capstone, which all of you are, something to think about too. You're getting a little secret pet peeves about analysts, right? What do you all think about? Have you both been panelists?
Yeah.
Oh, you are now? What do you think?
I agree.